Okay, 5.4, the natural and common logarithms, domain of logarithms. So to talk about this, we got to keep in mind the following, that logarithms were defined to be the inverse of exponential functions. So here's an exponential function. Let's look at a couple of things we know in terms of domain and ranges. We know that the domain of this was that you can plug in any x that you want, as long as your base was okay. So we did say that a had to be larger than 0. And then the range would be from 0 to infinity, because we had an asymptote for these. We had a horizontal asymptote at y equals 0. Okay, then based on that and the fact that logarithms are inverse to this, then the domain of the logarithmic function has to be the range of the exponential. So the range was 0 to infinity, so that is the domain for my log. And then this would be the range of the log, because that was initially the domain for the exponential. What they don't say in this little blurb over here, and I wish they had, is that the horizontal asymptote, if you swap your x's and y's, that means that we get a vertical asymptote here at x equals 0. So logarithmic functions will have an asymptote at x equals 0. So if you look at the function sort of quickly, you know that this is an asymptote. Okay, at 0 the exponential is 1, so at 1 you should get 0. So this is a rough sketch of what a log would look like. So keep that in mind as we progress through the notes. Okay, let's look at the domains real quick. So x minus 2, okay, so x minus 2 has to be larger than 0 for this to work, because the domain said from 0 to infinity, so it has to be larger than 0 to work. So that means that x has to be larger than 2. That means that there is a vertical asymptote here at x equals 2. Okay? Let me find my notes for a second. I think that's all I wanted to say there. Okay, how about x plus 3 over x minus 1? Okay, so x plus 3 over x minus 1 has to be larger than 0. Well, that's a rational inequality. You solve that by finding zeros over here. So x plus 3 equals 0, which means x is a negative 3. And x minus 1, make that equal to 0, so x equals 1. Put that on a number line. So start with the negative 3 to 1. Both of these are open because they need to be greater than. And then you test. So what happens here at 0? Well, just plug it in. So test at 0. You would get 0 plus 3. So 0 plus 3. So I'm testing in here. Divided by 0 minus 1. And that needs to be larger than 0. Well, that's a negative. So it's not true here. So it is true here. And it is true there. That means that the domain for this particular function is actually x is less than a negative 3, which means that there's a vertical asymptote at x is a negative 3, or the x has to be larger than 1, so there's a second vertical asymptote at x equals 1. Okay, next one. The absolute value of x minus 1 has to be larger than 0. Well, absolute values are almost always positive, except for one thing. Sometimes they are worth 0. So what happens, or when is it worth 0? Okay, when x is 1, you get a 0 out here, so that is actually not allowed. So x is not allowed to be 1. Other than that, anything else will work. So the domain here actually is, you could write it several ways. You could say, well, it's from a negative infinity to infinity, except x cannot equal 1. Okay, that would be one way to do it. Or you could say, well, x has to be less than 1, or x has to be greater than 1. So it doesn't really matter how you write that. What you do need to keep in mind here is that there is a vertical asymptote at x equals 1. Last one over here, if the base is a half, this still needs to follow the rule that it has to be larger than 0. It's similar to the absolute value. This is always larger than 0, except for x squared cannot be equal to 0, so x cannot equal 0. So the domain would be written the same sort of way. You could write it's from a negative infinity to infinity, except x can equal 0. You could write it with inequalities. You could also write it this way. It's all real numbers except x can equal 0. That means that there is a vertical asymptote at x equals 0. Okay, so that's a little bit about domains. So we talked about e being the natural base. So if the natural base is e, then the log base e would be the inverse of e to the x kind of thing, right? The log base e of x is the inverse of e to the x. Well, mathematicians are lazy. This happens so often that we have an abbreviation for that, so we usually don't write this one, we write that this way, ln x. Something else that sort of that comes out of this is the following: that if y equals ln x is inverse to y equals e to the x, then when you plug these things into each other, you should get x, right? Because the definition of an inverse was, so if a while back we were given, for example, f of x and g of x, and then when you plug one into the other, if that came out as x, you would say that they're inverse. And of course, to prove that they're inverse, you would have to do this both ways. Okay, so but that means the following. It means that if I plug this one into here, that if I say, well, so what is the natural log of, instead of x, write e to the x, well then this has to be x. And that has to do with this base thing over here. If this is an e and that is an e, then you always get this number. And the same thing works the other way around. If I start with this one, I say e to the power of x, but then plug in ln x in there. So if I use ln x over here, that also should be an x. And again, it deals with the fact that this would be actually the log base e of x. And that does give you x. When this base and that base match, you just get this one. That's actually going to be a rule down the line, and that rule would be written this way. If you have a log of a, if these bases match, you always get x out of that. Okay. So let's look at a graph of this thing. So find a domain. Well, x minus 1 has to be greater than 0. So x has to be greater than 1. That means I have a vertical asymptote at x equals 1. Graph f. Okay. This sometimes works a little bit easier if you write it this way. So I need to find some values for this, and I think it works easier if you think of it this way. Let's make this a y over 3, and then that's a natural log of x minus 1. So e to the power of y over 3 has to equal x minus 1. So e to the power of y over 3 plus 1 is actually equal to x. So based on that, I can make a table, but I'm actually plug in y values that I know that will work and get x values that I want to be able to graph. So hopefully these will make sense in just a second. So bear with me. So let's say that I'm going to pick a y value of 0. If I use 0, I get e to the power of 0 plus 1. Well, that's 1, and 1 plus 1 is 2. So when x is 2, my y value will be 0. If I use a y value of 3, I will get e to the power of 3 over 3, which is 1, so e plus 1. Well, that is about, e was 2.72, right? So that is 3.72. So at 3.72, my y value will be 3-ish. And then the last one usually that we work with then would be, what if you want this sort of to come out as a negative 1? So this was a positive 1. So if I used a negative 3 there, I get e to the negative power of 1. And that would be, so this, I think we said that, well, that's about 1/3, right? So we get 1/3 plus 1. So at 1 and 1/3, or 1.3 repeating, you should get a negative 3. Now let's see if we can put that whole thing into a graph. Now don't forget that we found an asymptote, right? We said there was a vertical asymptote at x equals 1. So x equals 1 is a vertical asymptote. And at 2, we were worth 0. And at 3.73, so 1, so that's 2, that's 3, that's almost at 4, we were up at 3. So 1, 2, 3-ish when we're somewhere over here. And when x was 1.3, so that is 1/3 past this thing, we were all the way at a negative 3 already. And then that gives you this value over here. Now, this is not the only way to do it, but I'll be honest with you, I struggle with these a little bit. And so I've sort of started doing it this way a while back. Because when I did this based on transformations, which is the other way to do this, I always messed it up. So I've gone to this way. So, but if you like doing this with transformations, you can certainly do that. Okay, determine the range and the vertical asymptote of f. Well, I already found the vertical asymptote for this over here, because I just did it based on the definitions. And then the range, well, it's an it's a log, so the range should be all real numbers, which we did get. So for C, we did get that the range was all real numbers. Find the inverse of f. Well, because I cheated and I rewrote it this way over that, I almost have an inverse already. I should have done this by swapping the x's and the y's. So let's see if I can recreate that. So we are going to write x equals 3 ln y minus 1. So we're going to do x divided by 3 is the natural log of y minus 1. And then if you want to sort of get rid of a natural log, then you have to use these things as exponents on e. That sounds awful. I'll just show it to you. So if I put e to the x over 3 and e to this thing over here, then we're in that rule that I just tried to show you over here, which means that if this base matches that base, you just get whatever is over there. You just get whatever is inside here as your answer. So I just get y minus 1 over here on this side, which is really what I was after, wasn't it? I'm trying to get this y by itself. So now add 1 on both sides, and then that will be the inverse. And then if you look back at what I have over here, notice that I basically had that already. And I think I did mention this a moment ago. I thought I'm using the definition of logs and exponentials and the fact that they're inverse to each other. Alright, use the inverse to confirm the range of f. So this is the inverse, and the range of f refers to the log. So the range of the log would be the domain for this function. So what is the domain for an exponential function? Well, the domain for an exponential function is all real numbers. So that means that the range should have been all real numbers. So those two match. And from the domain of f, find the range of the inverse. And the domain of f was over here, right? We said x had to be greater than 1. So if that's the domain, then the range for my inverse will be greater, y is greater than 1. And then it says graph the inverse. Okay, so the inverse is actually over here. So the inverse was y equal e x over 3 plus 1. Well, I basically have some points here that I can work with. The first thing that I'm going to do, and I'll do this in blue, is to graph it, is that if this was the vertical asymptote, then that means that I have a horizontal asymptote for my exponential at 1, which is why the range here said that it's greater than 1. Then the other thing is that you can just swap your points. So 0, 2, 0 here, this point is 2, 0, so that should be 0, 2 over here. And this point over here, which is like, what, 3.723, that would be then at 3, you should be at 3 points. So I'm just going to swap this. So let me write it over here in the function. So 3723 becomes 1, 2, 3, almost at 4. So that's 1, that's 2, that's 3. We're now almost at 4. So I get a dot over here. And then the last one was, we said here this was 1.3 repeating, or 1 1/3. So that gave me a -3. So that means that a -3, I should be at 1.3. So I should just be a third above. And so here you start seeing the exponential function take shape. Okay, so this one doesn't go up nearly as fast as the exponential functions we've seen so far, and that's because you're dividing here by 3. So every x value is only worth a third of what it used to be worth. Alright, so the common log, this whole stuff also works for the common log. The common log over here, so that's known as the common log, that's just the log base 10. Okay, and so this thing only exists if the inverse of that is true. So if there's an x equals to the 10 power of y, then we have a common log. And the pictures here basically deal with the same thing that I tried to show you a moment ago. So if this is given to us as the defined exponential function y equals 10 to the x, then 0, 1 becomes 1, 0, -1, 1 over 10 becomes 1 over 10, -1, and at 1 you should be at 10, so at 10 you'll be at 1, and you get the log that's tied to its exponential function. So the domain works the same way. X plus 2 has to be greater than 0. So x has to be greater than a -2. So you would have had a vertical asymptote here at x is a -2. Find the inverse. So maybe first start by writing this as a y. Then swap your x's and y's. So need to divide over here, x to the divided by -2, it's log y plus 2. So to get rid of this, you need to put these as exponents on a 10, because by matching this, because remember that log means log base 10, so by matching these two bases, the y plus 2 sort of just drops, so you get y plus 2 is equal to 10 to the power of a negative x over 2. And then the last step would be that the inverse of x would be, I need to subtract this 2 on both sides. So -2 plus the log, not the log, -2 plus the exponential base 10 negative x divided by 2. Okay? Let's look at solving some of these. Sometimes we'll use inverses, sometimes we'll just use definitions. So if the log 2 of 2x plus 1 equals 3, then that means that the base 2 to the exponent listed there has to be equal to 2x plus 1. Well, we know what that is worth. That's 8. So if that's true, then 7 is equal to 2x, and that means x is 7 over 2. Over here we get x cubed is equal to 343. So some of you know a number cubed that works. So if you're not sure, you would have taken the cube root on both sides. So that means x is the cube root of 343. And that actually does come out as a 7. Okay, how about here? Well, you got to isolate first. So we do have to divide by 2 first, so that I get e to the power of 3x is actually equal to 3. And then here we can work this different ways. So if e to the power of 3x is 3, then the log base e of 3 is equal to 3x. And that's commonly written as ln 3 is equal to 3x. So just divide by 3 on both sides. That means x is ln 3 over 3. Now your calculator has an ln button, so you could put that in the calculator. Make sure that you put brackets around this 3, so that it takes the natural log of 3 and after that divides by 3. And then this comes out approximately as, let me find my notes, 0.366. So 0.366. Okay, so that's one way to do it. The other way to think about this would be to get an exponent down with if it's an exponent on a base e, you would take the natural, or you would take the log base e of e to the 3x on both sides. So the log base e of 3, because if these bases match, you just get that part back, and then usually we write this as ln 3, and then we're back over here. So that's the same reasoning, sort of, but a slightly different approach. And I don't really care which one you do, sort of work with both of them actually at times, because sometimes one will work better than the other. Okay, over here you need to isolate as well, so don't start taking any logs yet, so we need to subtract 3, better do that correctly. So then divide by a negative to get rid of the negative, so we just have the base 10. So we'll do it the other way first. So the log base 10 on both sides will bring the 4x down. So 4x is actually log base 10. Well, we don't write that 10 anymore. It's just a common log. And then we get log 11 over 4 as our answer. And that is worth approximately, well, this should be about 1, so this should be close to a quarter. So if you put this in your calculator, the button on the calculator that says log is the common log. So if you put that in the calculator, you should be able to get 0.26. Okay. Oh yeah, and on tests and quizzes, I often don't give you your calculator. So this would be the answer then that you would be stuck with, which is fine. Initially, give me both for a little bit on your homework. Get used to using any calculator on this and being able to write it just as an accurate number. And then this is a quick little recap of the whole thing over here. So if a is larger than 1, we get an interval for the domain from 0 to infinity, and the range is from negative infinity to positive infinity. That would also be the case if the base here is between 0 and 1. Now we haven't done much with this, but so this one refers to the following. And we'll look at both of these. So if I have a to the x if a is larger than 1, so if a is larger than 1, then it would look this way, right? Still 0, 1. If it's at 1, you would get the value a, so that would be up, and then at a negative 1, you would get the fraction value. So this is what a to the x looks like, which is an increasing exponential function. When a is less than 1, remember these two things flip-flop. So we still get this point, but this point is now mirrored over here, and this point is mirrored over there. So we get the decreasing exponential function. Well, these flip-flop as well. So, but they flip-flop across the x-axis. So this point ends up over here, and this point ends up over there. And so you get a second log function that looks like that. Now, I'll be honest with you, I am not very good at these. So I struggle with this a little bit. So when I have to deal with this and graphing it, I usually do the little thing up there when we work with the natural log. So if you gave me, for example, y equals the natural log, or it has to be a smaller base, right? So if you, for example, give me the log of a half to the power of x, I'm going to do this. I'm going to say, well, that means that a half to the power of y is equal to x. And then that way I'm just going to fill in for y values that I know. So I'm going to fill in, for example, a y value that I know, 0. Anything to the power of 0 is 1. So I'm going to hopefully get it this way. And then if I use a y value of 1, I know that I would get a half. And if I used a y value of a negative 1, I flip this thing, so that would give me the 2, and then I would graph it over there. Now let's see if it worked. So at 2, I should have had the negative version, which I did get. At 1, I should get 0, which we got over here. And at a half is where you get your 1. So that's how I'm going to approach those, primarily because I struggle with this. So this is what I've sort of incorporated in doing it so that I can still get these right. Okay, thanks.